more common in, I think it's more common in girls, like if you wear like.
Okay.
Yeah, I know you
All right, so let's get our notes out and let's go to number 1. We haven't gotten through all the classical curves yet, but we have started a good conversation, and we're now ready to do problems 1 and 2 and 3 and 4, pretty much. So we're going to sketch on a calculator. We're not going to do all of these because we did a few the other day. Let's put our calculator in radians per the directions. Let's set our window from 0. Oh wait, I got to be in polar. I go to polar mode. You probably still are. I am not. Okay. Now, let's set our window from 0 to 2 pi. We're in radians, so we discussed the other day our steps should be about 0.1, 9.13, that's fine. And let's set our x's, let's do -6 to 6. And the same with our y's. That should give us nice pictures, at least for these first few. All right, let's type in our first equation. 3 sine 2 theta. And did you get a graph that you expected to get after our conversation last time?
Yes.
Yes. You got a rows. Look at all the equations in number 1. That's the format of a rows equation. It has 4 leaves or 4 petals. Did you expect that? Yes, for reasons we discussed before. And it's kind of hard to tell because it's on the diagonal, but you know how long those leaves are, right? They are 3 units long, okay? Now, if we changed the sign to a cosine, thank you. If we change the sign to a cosine, I'm going to have you do that in a minute, but you already know what's going to happen. What's going to happen? You're going to get exactly the same picture, but it's going to be rotated. So let's just try it and see. So we're at 3 cosine 2 theta. And because of the rectangularness of our screen, things might get a little stretched one way or the other. You can always get a better picture by zoom square. So zoom 5, and then you can see your leaves are actually the same size. They didn't really look that way in the beginning, but they are. Okay, so I'm not going to sketch the rest of those with you. You can graph the rest of those. Let's look at number 2. Without sketching, describe it. A and B are both roses, right? Something cosine something, something sine something is going to be a rose, okay? So we got a rose. What about A? What can you tell me about the rose?
20 leaves.
His leaves are 14 units long, and there are 20 of them. And then what about B?
9.
They are 8 units long, and there are 9 of them. Now, just a little FYI, something for you to think about. If I were going to graph, and I am not, we don't have time to do it right now. If I were going to graph the equations in A and B, I would need to change my window. Because right now my window is -6 to 6, which will accommodate leaves that are 6 long. If the leaves are longer than that, then I'm going to have to make adjustments to the size of my screen, right? Okay, now let's look at number 3. 3 is not a rose, or none of those in 3 are roses. Why not? They have a what? A plus or a minus. It could be a minus, either one. These are all pluses, but it could be minuses. If the equation looks like those in number 3, it is not a rose, it is a limousin, okay? Now, I do want you to graph all 4 of those. So real quick on your own, you can use the same window we had, it'll be fine. using the same window, go ahead and graph those three. And just make a little sketch underneath, because they're kind of, so you can remember what you got. Make yourself a quick little sketch. Okay. Do all of your graphs have similarities?
Yeah.
All right, so let's talk about some differences. What are some differences you noticed between A, B, C, and D?
Well, like, in that.
Liam?
A was more like circular.
A was quite circular. Did you notice anything about its positioning though? It wasn't like positioned around the origin, was it? No. In fact, how far down did it go? What was that low point down there? 2 or -2? Yeah, okay. And can you tell what the high point was for that first one? 4? Alright, so let's just throw that back on. Okay, so what are some other observations? Yeah?
Like, I'm not sure what you call it, but the little kind of like indent
Mhm.
part got more pronounced the bigger the coefficient was.
So B had an indentation that you could see, right? Where was that indentation? How far down was it?
Very bottom.
-1.
Down at -1? Where was the indentation in C? At 0? Okay, and then there was an indentation in D, but it was actually so much of an indentation, it actually went into the figure and had a loop in there. And I don't know if you remember, notice, but the size of that loop was 1. The little indentation was like 1 bit. Let's look at the coefficients and let's talk about something. Look at A, the indentation, and it was hard to see because it was quite circular, but there is an indentation, very flat, I'll call it flat, but it was down at -2. And in B, the indentation was a little more pronounced, but it was down at -1. At C, it was quite pronounced, and it was at 0. And at D, it was so pronounced that it actually went into the inside. So are you noticing something about those coefficients? If we call like this A and this, I'm doing rows, if we call this A and this B,
B minus A.
so the indentation is gonna happen at B minus A. And if B is bigger than A, then that means the indentation is going to be inside the figure. You're gonna have a loop in there. Okay? Now, if B and A are the same, we talked about this yesterday, if B and A are the same, then we have a cardioid because the indentation is right there at the origin. And that's a cardioid, an indentation at the origin. All right, we're not gonna do all of these, but we did signs. Change one of them to cosine. Change D to a cosine. Change D to a cosine and tell me what happens. So is it the same shape? Yep. But what happened? It got rotated, which is exactly what we
When we say
expect.
rotate, do we need to define if it's like rotate? Is it being rotated on the X or the Y axis or by like 90 degrees? Like what is it?
It's being rotated 90 degrees, just like sines and cosines are. Okay? Now, what do you think would happen if we took, go ahead and do it, take the picture you just graphed, which was 3 plus 4 cosine theta, make that a minus. I think we talked about this yesterday, but let's do it again. What does 3 minus 4 cosine theta look like? Same picture exactly, but flipped. So upside down. 180 degrees, just like you would expect. All right, let's turn the page. That's about it. We've now discussed roses and limacons. We know what their equations look like, and we know some characteristics about them. So now we're moving on. Does this equation look different to you? That part looks like a rose, but you had a square, so it's no longer a rose. I wonder what this one looks like. Well, let's leave our window set exactly as it is, but in order to type this in, aren't I gonna need to take the square root? And when I take the square root, kids, it's always plus or minus. So I'm actually gonna graph the positive square root and the negative square root. So I'm gonna graph 2 equations this time. I can use the same window I had before. So second square root. And negative second square root. Now, I do not understand this. I'm sure there's a reason. It's somebody, you can Google it, or maybe like Rushka or somebody smart knows. I'm not exactly sure why this is. Those are supposed to be connected. This picture actually looks like this, and I'm not sure why there's that gap in there. There's a reason, I just don't know what it is. This shape, what does that remind you of?
Infinity.
Oh, an infinity symbol or a figure 8, right? It is called an equation where it's r squared equals basically a rose. R squared equals a rose. That's called a lemniscate. And this is really dorky, but remember how I told you I remember a limacon because it's a lima bean? I remember lemniscate figure 8. Now, it's not pronounced lemniscate, but that's the way it's spelled. So a lemniscate is a figure 8. Now, how long are the leaves of that figure 8? Does that make sense to you?
Square root.
Square root of 9. Didn't you graph the square root of 9? And it's just like a rose. That neat number out there is a 3, so the leaves are going to be 3 units long. Go ahead. So a lemniscate is always going to be this style of equation. Now, could I make this a sine? Absolutely. If I make it a sine, then guess what happens to my figure 8? It rotates, okay? It's always going to be r squared equals a number, sine or cosine, 2 theta. Okay, that's what the equation is going to look like. Could you make up your own equation and do another format? Yes, you could. But the classical curve itself, the lemniscate, is always going to have this format, some number, sine or cosine, 2 theta, r squared. Okay? So, what do you think B is going to look like? It's gonna look exactly like this one, except the leaves are going to be 4 units long. Right, does that make sense to you? Okay. Alright, so that's a lemniscate. Now, take a look at the equations in number 6. Wait a second, guys. Tell me about the equations in number 6. What's different about them? What are they missing?
Sine or cosine.
They're missing a sine or a cosine. Now, that is going to have a very significant impact because with all the other curves, we were able to graph between 0 and 2 pi because they all involve sines or cosines, and the period of the sine and cosine is 2 pi. What does that mean? When I say the period of the sine is 2 pi, what does that mean? Every 2 pi, it just repeats itself. So if I graph from 0 to 2 pi, that will be the picture. If I graph more than that, I'm just going to repeat myself, right? I'm going to go over the picture. I go around and around and around. That is not the case with these guys, all right? So here's what I need you to do. I need you to go to window, and our theta min is going to be 0 still, but our theta max, let's make it 12 pi. Leave your step the same. In your x min and max, let's make it negative 80 to positive 80. We'll talk about y in a second, but let's just get this picture drawn. So x and y are negative 80 to 80. And we're going from 0. I forgot now, did I say 12 pi?
It's not one of those.
All right, so now you type in your equation, which is just 2 theta, and press graph. What do you get?
Whoa.
A spiral. Now, I want you to watch that spiral real careful. I want you to look at it. Notice that it spins around exactly 6 times. Because when I set my window 0 to 12 pi, I told the calculator to go around 6 times, didn't I? Yeah, because what's around once? 2 pi? So that took me around 6 times. If I make that number bigger, it's gonna spin more than that. Now, why did I choose negative 80 to 80? Well, my biggest theta is 2 pi, or 12 pi, which was about 37. My equation is 2 times theta, so I was going to about 74. So I just said I'll use 80 and negative 80. Does that make sense to you? So if it had been 3 theta, I would have to make it even bigger. All right? This equation is called, R equals 2 theta, is called a spiral of Archimedes, or an Archimedean spiral. Archimedean spirals, and you watched your calculator do it, they start at the pole and spin out. That's what a spiral of Archimedes does. It starts at the pole and spins out. Because obviously, if theta is 0, R is 0. That's your first point. And then it just goes around from there. Now, I said 12 pi, okay. Now, I need you to change your window. Play with this for just a quick minute. We're using the same thetas. this is 2 right there. Yeah, okay, so for theta min, or theta min max are the same. For your x's and y's, use negative 0.1 and positive 0.1. So in other words, you're establishing a very small window, negative 0.1 to positive 0.1. And then type in your equation and graph. It takes it a minute. Now, let's go ahead and change theta. Let's go to 20 pi. So 0 to 20 pi and graph that.
I'm not kidding.
Okay, so what happened this time? Where did it start this time? Out here, right? And it took it a couple minutes, but you finally saw it. It was like spinning around in space for a while, and it finally came in. And it's going to keep spinning as many times as you tell it to spin. So when I set it to go 10 times around, that's how many times it went, and then it stopped. It can go 30 times around. It can go around as many times as you want. This is called a hyperbolic spiral. And a hyperbolic spiral starts out and spins in. That's the difference, the direction of that spin. Will a hyperbolic spiral ever touch the pole? No, why not? Because theta cannot be zero. Right? This or R cannot be 0. This will never equal 0. This cannot equal 0. So therefore you're going to keep going and going and going, but you're never going to get to the pole, whereas that's where an Archimedean spiral starts.
Are these like, I don't know if this makes sense, but are they like infinite? In a way, like does it just keep
Yeah,
spinning
it's going to
out?
spin as, when you graph it, you have to put a theta max in,
Right.
and that stops the spin, but otherwise it keeps going forever and ever.
I didn't get it.
Okay, we'll have to work on it. All right, without your calculator, describe this equation. Without your calculator, describe this equation. All right, wait a second. Does the equation itself look like one of our classical curves? No. No. You need to recognize the general format of a Rose equation. Somebody give me a Rose equation. R equals 3 cosine 8 theta. That's a Rose. How about a Lima sign? R equals 3 plus 3 sine theta. How about a lemniscate? What do I know about a lemniscate? R squared equals 25 cosine 2 theta. And what about a spiral? R equals 2 theta or 2 over theta, right? Depending on which kind we've got. This is not any of those. So let's take a closer look at the equation. Would you agree that this could be written this way? Is that the same equation? Now get out your reference sheets for chapter 5. Maybe you already know this one. What is that? That's a formula for something. That's the sine of 2 theta. This is the formula for the sine of twice an angle. 2 sine cosine. Well, what's the angle? 2 theta. So this is a formula for the sine of 4 theta. And there's 3 of them. Now tell me what it is.
Sine 12 theta.
It's a rose. whose leaves are length of 3, and there are 8 of them. Yeah, there are 8 of them. So when you thought, when you left chapter 5, that all of that junk was behind you, it is not. It's still all there. This 8 we've already talked about. What's the difference between these two?
Rotated by 9.
They're exactly the same shape, but they are flips of each other. So I don't know, I should know this, but I don't. I don't know if it's sideways or up and down, but they are flips of each other. What shape are they? They're special lemmasons called cardioids, right? Okay, before we do this, I wanna answer some questions. Let me see how much time I have. Okay, not much. I have to do at least one symmetry problem, but before I do that, what questions do you have? First of all, I have a huge apology. One of the homework problems I corrected on my sheet and did not correct on yours. Let me find it. On 6-3, number 3, it should have said x equals 2 cosine and y equals 2 sine. They shouldn't have both been y's. One should have been an x. Some of you changed it on your own, God bless you. Some of you tried to figure out what in the heck I was talking about, and I appreciate that too. I do want to talk about that problem though, because
I figured it made more sense.
No.
okay, now it says certainly, we could do this problem on our calculators, putting it in parametric mode and graphing it, right? But it says no calculator. So you can handle it however you want. But I like to, if I have to graph something, and it's in parametric form, I like to change it into Cartesian form, because that's how I graphed my whole life, in X's and Y's. And we did this. Remember doing this? We square everything. So we're gonna end up with adding them together. We're gonna end up with x squared over 4 plus y squared over 4 equal 1, which is x squared plus y squared equals 4. So some of you that made this change, thank you for doing that, said, okay, that's a circle centered at the origin with a radius of 2, and you drew that picture. And then what did I do? I didn't make a big X. I didn't need to make a big X. I crossed this part off and drew a circle, around, around this. Because what does that tell me? It's a half circle. Because we're only letting t go from 0 to 180. Does that make sense to you?
Yeah.
Yeah. Okay. Perfect. All right, what else? What other question you have? Either about the quizzes I turned back or some homework paper I turned back. Something. Ms. Macaulay.
Can you do number 5 on 6-3?
6-3, number 5. All right, so I gotta write some equations here. First of all, so 4 feet above the ground with an initial velocity of okay, so x, when I write my regular projectile motion formula, there's my regular projectile motion formula, and certainly my baseball is a projectile. Normally I would just say let x equal t, but my x's have been altered by this 30-degree angle with the horizontal. So my x is r cosine, what was my angle? 30 degrees, t. That's my x value. 120 is the speed, magnitude, so it's R cosine t. Alright, and then my y is gonna have my negative 16t squared, but my y component has also been changed. So what's this going to be? 120 sine 30t, and then what was my initial 4 feet above the ground? So here are our parametric equations. Alright, so my x has been altered and my y has been altered. Alright, so here we go. Does the ball clear the fence? Did you graph it? And what's it look like when I graph it? By the way, if I'm going to do this now, I need to go back to parametric mode. And my clear out those things. And I've got 120. Oh shoot, these are the ones you have to be careful of when you put in. 120.
Yeah.
Sine 30.
Always 6.5. But this is on the 0 point.
Negative 16 t squared plus alright, so my window has got to change.
Where's the examples of how to write the It's on the little lab. It's on this line. So it's physically significant if you're rejecting. The curves that were you disregard accepting
Okay, you gotta change the degrees too, I forgot to do that. So that messed that up. Now I got it. Okay, gotta set it in degrees because that 30 we put into the problem was degrees, right? So I didn't change that. So now I got my parabola, okay? I got a nice little parabola, which is exactly what I expected to happen. So I'm gonna hit trace. And I'm just gonna go out 350, so I'm gonna let x be 350. And when x is 350, the ball is 22 feet above the ground. Okay, just by tracing it. So how tall was the fence? 30 feet. Is it gonna clear the fence? No, because by the time it gets there, it's only 22 feet high. So if so, well, it doesn't clear the fence. If not, could the ball be caught?
No.
Alright, I am not an athlete, okay? 22 feet seems a little bit high, right?
Off the fence, that's what I'm saying. I thought they were into it.
Yes, because it's too high to be caught, but it's not high enough to over the fence.
This is kind of back earlier in the problem, but on y equals like that equation right there, y is like, I know the initial velocity is 120 like feet per second, so why is it 120, like why is the sine 30?
Because it's at an angle. We're not dropping it straight down, we're not throwing it straight out, which is what we were doing before. This is at an angle, and that angle has to be accounted for. So you're looking for the components of the velocity vector. The components of the velocity vector are right here. Tess? I can't hear you. Yeah. Yeah. And together they make the parabola. All right, we'll do one more, quickly, one more, from either the quiz or something else that you got back. Sydney?
On the quiz with one heart, did you do number 2?
Okay, so we've got we've got 3 points and and we wanna find the measure of what angle? I wanna find the measure of angle C. Okay, so if I have 3 points out there, if I have 3 points out there, then certainly they make a triangle, as long as they're not linear. They make a triangle. And angle C is created by this vector and this vector. So the coordinates of this vector are 3, 4. And the coordinates of this vector are -2, -2, 12. So I dot those 2 vectors, and I set that equal to the magnitude of this times the magnitude of this times the cosine of the angle. Okay, and then you get the cosine of your angle. The second cosine that. So I don't recall seeing those vectors on your paper, but that's where you gotta start. You gotta start with the vectors. Okay? Now, quickly, we need to look at our notes. We have one more thing to do in these notes, and I wanna talk about it for a second. So, you do not need to memorize these tests of symmetry, okay? You need to be able to use them, but you don't have to memorize them. All right, you clear on that? So, for example, in number 1, when I am going to test this equation for symmetry about the x-axis, I'm going to take out the r and the theta. Those are that's like my x and y when I was doing tests of symmetry before. And I'm going to replace it with, well, this one doesn't get replaced with anything, and theta gets replaced with a negative theta. And then I gotta remember what happens when I take the sign of a negative. What happens to that negative? No, it doesn't go away. It only goes away in a cosine. In a sine and a tangent, it comes out to here. So this would become 3 plus 3 sine. Is that the same equation that I started with? No. So that test of symmetry didn't work. However, there's another test, and so before you say no, you have to check the other one. So all of these have 2 tests. Check the first one. If it works, you're moving on. If it doesn't work, you have to check the other one. So the other one is going to look like this. I'm going to replace r with negative r and theta with pi minus theta.
Wait, this is 4.
Yes.
On the first one, when you're on the y-axis, right? It says negative r and negative theta. And then it goes r.
Well, I might have said y-axis, I meant x-axis.
Oh, you meant x. Oh,
yeah.
x.
Oh,
Okay.
I'm sorry, yeah, okay, I'm sorry, I didn't read my question. I was gonna test them all, and I just started with the top one. But anyhow, that's good enough. So, I did not do the problem on the paper. I did x-axis. The point I'm trying to make is, this is easy, you just plug stuff in. If the first one doesn't work, then you gotta go to the second one. And the second one is gonna involve a formula from your reference sheet. Because this is the sign of an angle minus an angle, right? So you'll have to expand all that out with your formula and see if it matches. All right, I want you to go ahead and try your homework for 6-5, and I will do one from the homework next time we're together. Okay? Oh, some of you, if you're an NHS applicant, I got some of your things done here. Save myself some trouble.
Yeah. feel like there should be like she doesn't have a
I don't have all of them done, I got some of them done.
Yeah, dude. Absolutely.
Excuse me.
Sorry, I thought you said my name.
I did, but whose desk is this? Not you. Lillian? Coleman? Zoe?
Is it just for the people that got email?
Yes, those are the people I have done. Let me see what the right answer is. See if we have the- So you have the wrong answer. Cosine negative 68. Wait, why is it 12? There's 14.
Oh, yeah, I forgot.
Always.
Can I shoot up an HS for Andrew?
He can come in.
I am.
He can come in.
Okay.
Yeah, perfect, thank you. I have a test. Guys, you need to get your walls up. Walls up, phones in the pockets. Phones in the pockets.
Now or would you rather?
You get it. Something else said.
Oh, I was waiting on you wait 2 weeks.
Get your walls up. Come on, let's go. We got a test. What? I hope I turned this off.